If you were in words and without any numbers to describe the velocity and acceleration of the package, what's its acceleration going to be? The package after 2 seconds. Gravity, yeah. Okay. Shh, listen up, guys. Yeah.
I bet I keep stopping the whole thing, but like, how did you incorporate the 2 seconds into C? I don't honestly.
Oh, I'll put that in for the time. So when I solve this, it'll end up being half of 15 times 2 squared. Yeah, so it'll be like 30 meters apart. Okay. All right, so let's just do it. Let's just do this. What's the initial velocity of the package? 30 meters per second, yeah. Right, because it was moving up at 30 meters per second with the helicopter. What's the acceleration of the package? 9.8 or 10 meters per second squared, but in the opposite direction. So we want to know how fast it's going, right? Its velocity after 2 seconds. And so if you look at your formula sheet again, it's just the initial velocity plus the acceleration times the time. We know the time is 2 seconds. So you get 30 meters per second plus a negative 9.8 or negative 10 meters per second squared times 2 seconds. And so that's like 10.4 meters per second. And it's positive. What does that tell you about the package? It's still going up. Yeah, 2 seconds later, that package is still moving up. Even though the rope is cut and the helicopter's not lifting it anymore. Why would it still be going up? Yeah, it's inertia, right? It was moving pretty fast. It still wanted to move in that direction. And it's going to take some time to get rid of 30 meters per second in speed upwards. It's going to take about 3 seconds. Yeah?
The time says, it says 2s.
Oh, yeah, sorry. That's 2 seconds.
Oh, dear.
Yeah.
So with the original thing, the rope was 5 meters between them. So that means after the 2 seconds, it would have been inside the helicopter. Right? Because it was going up that fast.
Well, don't forget that the helicopter is still accelerating upwards.
The helicopter stopped moving.
Okay. All right, any questions before we move on to the next one? Okie dokie. All right, so we've got this. This one, you know what? I read too fast, and I missed part of it. So let that be I don't know, a learning thing for you. Make sure you read these really carefully. What forces are acting on the elevator car? All right, there's the force of gravity, and there's... Which way is it moving?
Friction is moving with gravity.
Yeah, why?
Gravity is moving against the friction doesn't matter. Yeah, it is.
Well, it's because the car is moving upward, right? The car's moving upward, so friction would act against that, it would act downward. And so we've got a force of friction to deal with as well. Okay?
Wait, how is this friction in that?
I don't think we've ever dealt with friction on the...
Look, guys, it says the 2 guide rails for the elevator shown above each exert a constant friction force of 100 newtons on the elevator car when the elevator car is moving upward. So we've got to include it this time.
So will that affect anything as far as, like, since this is the first time we ever had to deal with a body diagram where 2 forces go in the same direction?
Yeah, if you had to analyze this as a system, friction would be an external force, and so it would be part of the net force.
Oh, okay.
Okay? So, yeah, that would be the difference. All right, guys. This next question is worded a little funny. Okay? because they've taken a question and tried to adapt it to make it look AP Physics B-ish. I'm sorry, AP Physics 1-ish. They didn't tell us what the breaking strength of the cable was. Right? So we wanted to determine the maximum upward acceleration of the elevator car without snapping the cable. Yes, sir.
For the first one, this might be like a dumb question, but did we even answer the second part, the identifying the source, or is it just like a free body diagram that tells you that?
Oh yeah, if we would have put just the numbers, then we wouldn't have really identified the source. But since I said F sub g, we know that's gravity. And just for giggles, how much gravity is there?
4,000 newtons.
4,000 newtons. Okay. How much friction is there? No, there's not. There's 200. Each exerts that force, so it's 200 newtons. Okay. So that's where you have to read carefully. That's where I made a mistake earlier.
Wait, how do you know it's 200 newtons?
Because each of the two rails exerts a friction force of 100 newtons.
Okay.
Okay. I don't like it. Okay. So guys, in terms of our free body diagram, what is our acceleration?
2 meters per second.
When we substitute the breaking strength of the cable for tension, point at which you're in big trouble, right? And that'll be the maximum acceleration you'd be able to have. Bathroom scale. Under what conditions would that scale read your actual weight while you're on the elevator? That's one condition, when it's not moving. When else will it read your weight? When what's constant?
The rate of the elevator?
The velocity of the elevator. Because then there's no acceleration. Okay. When are you going to get a reading that's heavier than your actual weight?
When going up.
When you're accelerating upwards.
Right.
So that happens in two cases, though.
Wait, what?
You accelerate upwards when you're moving up and you're gaining speed. When else are you accelerating upwards? Yeah.
Downward and losing speed.
Exactly. Yeah. You know when you go down an elevator, you feel heavy right at the end,
Oh, yeah.
right? That's because you're accelerating upwards, and there's more normal force upwards to stop you because of your inertia. And so the opposite is true when you're feeling lighter. Right? When you're going up, but then it slows down, you get a little lightheaded, right? Or when you start dropping, also the same deal. Wonderful. One more. Can we fit it in?
Sorry, storage problems.